Hey guys, Redox here with another video on Riemann sums, part 2. This is going to be finding the area under a curve. So on the top left, as you can see, there are 4 different formulas. On the area formula, you probably already know, it's pretty simple, just length times width. You should probably know it if you're in calculus by now. The one below it is the width equation. This is how to find the width of each rectangle under the curve. The width is always going to be the same for each and every rectangle that you find because the width has to always be uniform. Now, this is created through using this formula. Delta x represents the so you're given an interval with the graph that you're supposed to find the sums of. So delta x is just the difference between the endpoints in the interval, and then n is just the number of rectangles that you're supposed to be calculating for. As in the top left, the uppermost left equation, that represents the upper sum, and so the upper sum is an equation that finds what the right endpoints are for each graph. And so the a value represents the first endpoint in the interval. The I is remaining as a variable the entire time. Delta x will just represent the same as the width or the change in the x values for the interval, and n is just the number of rectangles. And then the one below it represents the lower sum, which is the same thing except I is replaced with I minus 1. Okay, let's get started. So in this video, we are starting with y equals root x. So for this equation, you don't really need to use Riemann sums all that much because it's a pretty simple equation, and you're given the amount of rectangles and you're given most of everything. So let's just solve it without, or try to solve it without. So now we need to find what the width is. So the width is delta x over n. This interval is from 0 to 1. So that means the interval is 0 to 1. And now we know what the interval is, so we can find the delta x, which is just 1, and over the number of rectangles, if we count, there's 1, 2, 3, 4 rectangles. So 4, which is the width. Now we are good. This is the width, 1 over 4. Now we need to find what the actual lengths are of each rectangle. So each length of the rectangle is constantly changing every time you move left or right of the graph under the curve. So we have to take that into account when choosing what the lengths are. So to find the upper sum, we're going to start with the upper sum. We have to do a, which is just 0. And this upper sum essentially finds the x value that you can plug in back into this equation. The upper or lower sum just finds the x value. So a is 0 plus I, which remains the same. This is the numbered rectangle, so as we have 4, I is going to change from 1 to 4. Delta x is just going to be the same, so 1 times 1 over n, number of rectangles, 4. So the upper sum, or x value, is going to be I over 4. Okay, so now we know what the x value is, and we know what the width is. Let's calculate. So to find the area, we do length, or actually we first start with width. So since width is the same, we can just do one width, and we can multiply it by all the different lengths. So they will be in this parentheses, and distribute it amongst all of the different lengths. So we have 4 rectangles, so we can most likely calculate what the lengths are. So before we do that, I would like to go over why we need the equation that we are given, y equals root x. Well, since this is the x value that we found down here, the upper sum, you plug it into the equation. So y equals root I over 4. Which makes us think that all of the x values that we capture or all of the I values of the rectangles will all be under root I over 4 for the Y values. So we can just start with when I equals 1. So this rectangle right here. So this one we can start when I is 1. So this one will have 1 over 4, which is just 1/2. This one is 2 over 4, which is root. I'm drawing too small, but let me draw it down here actually. So 1 over 4 for the first rectangle, root 1 over 4 actually. You have to root the entire equation. Root 2 over 4, because it's the second rectangle. Root 3 over 4 is the third rectangle, and lastly root 4 over 4 because this is the last rectangle. So now that we have all the rectangles taken into account, we can plug them into this right here. So we have to add all of them because we're using sums, and that's the main part of this unit. So it's 1 over 4. So what do you think 1 over 4 down here on the bottom left is? That's just root 1 over root 4, which is just 1/2. So this is just going to be 0.5. Oops. 0.5. Now, for this next one, this is equal to root 1 over 2, which means it's just root 0.5 plus root 0.5. And as you can see, you probably need a calculator for this portion. Next, we have root 3 over 4. So this is just root 3 over 4. So root 0.75. And lastly, we have root 4 over 4, which is equivalent to root 1, which is just 1. So now let's plug all of these values into a calculator, and you will most likely get approximately 0.7668. This is rounded, okay? So that's approximately what you will get by just using all these values. And yeah, so that's this problem. Or actually, we're not completed, right? Because we only found the upper sum. Now we have to find the lower sum. And the lower sum is significantly harder than the upper sum. So just keep that into account when thinking about which one to choose if you're given the choice, obviously. If you have to do one of them, just do one of them, alright? Or if you have to do them, then just do it. Okay, now let's move on to the lower sum. Okay, let me erase all this. Okay, now, the lower sum. So we already know that the width is 1 over 4, because we calculated that in the last part. So now we have to calculate the lower sum from finding the lower sum, which is this little s in the top left. So calculate that by saying that the sum, or x value, is the same thing. It's equal to, oh, I forgot to say this, but like I think I did say it, but the upper sum finds the right endpoint of the rectangles that I'm highlighting right here. The lower sum, or actually the upper sum finds this value. So there's two types of triangles that, or two types of rectangles that you can use to find these equations. So there are the ones in light blue, and then there's the ones in dark blue. I don't think they're really even, but it's fine. So the ones in light blue will essentially calculate the so the ones in light blue calculate the lower sum. So the upper sum that we just found are these dark blue ones. It's hard to see, but it's fine. So the dark blue ones take up all of this extra space outside of the curve, which is why the actual area is going to be less than what we found from the upper sum approximation. And now the lower, which is why it's called upper sum. And now the lower sum actually takes up less of the area, and so it's under calculating how much area. It's taking out this gray spots that I'm highlighting. It's not accounting for them. It's not accounting for these extra spaces, so it's going to be lower. So this is why we must calculate both of them to find an approximate for what the area might be, so it's more accurate, of course. So we calculated the right endpoints. Now let's calculate the left endpoints using the lower sum in the point of view of the light blue rectangles. Now let's continue onwards. So we will start with finding I minus 1. We're just going to leave it like that. And A is the same because the interval is still 0 to 1. So it's going to be 0 plus I minus 1 times delta x, which is just 1, over number of rectangles, which is going to remain the same for both of the sums, so it's just 4. So this is going to equate to I minus 1 over 4. Alright, so that's what the lower sum is. Now let's plug it into the equation once again, and we will find out that it is I minus 1 over 4, which is repeated over 4 times for I. So we'll do the same process. We'll plug in 1 for I, 2 for I, 3 for I, 4 for I to account for all 4 of the triangles that we're finding. So when we plug in 1 for I, it's just going to be root 0 over 4, which is just 0. Now when we plug in 2 for I, this is a little confusing because remember here, it's I minus 1. So when we plug in 2 for I, it's going to be 1 over 4. So we're essentially calculating less than what we did last time, because we started with 1 over 4 last time. Next, we're calculating when I is equal to 3, so that's 2 over 4. And lastly, when I equals 4, which is 3 over 4. Or 4 over, wait, when I equals 4, it's root 3 over 4. Sorry, that's a little confusing. So, even for me. So now, we will put these all in the equation. So, area, once again, top left, you should know this, length times width. Since the width is the same every single time, just gonna plug it in right here, and all of the points that we found down here will be put in there. Now, root 0 over 4, it's just 0, right? Root 0 is just 0, plus root 1 over 4, which is just 0.5, or 1/2. Root 2 over 4 is just root 0.5, because it reduces to 1/2. And then lastly, root 3 over 4 is just root 0.75. Now, I don't have the exact values for this, because I'm too lazy to find it, so this is what we're going to come up with. So, once again, now we know that the area is between the lower sum, which is this, and the higher sum, which is 0.7 something something. Alright, we're done with this problem now. Found both the sums, and now I'll move on to a more complex one. Oops. I edited this a little bit. Alright, now let's move on to the next one. This one might take a little bit longer, but don't worry, it's not going to be too bad. Actually, it might be, but so this next problem, it's a little bit different because we're not given one of the values that we usually get. Let me show you. Let me choose a practice problem that we will solve. Okay, so we will be solving using limits in this scenario, which is a little bit different than what we were doing, and you might be wondering, how might we implement limits in these problems? Well, let me tell you, it's not going to be so fun. So for this part of the portion, I'm only going to do upper sums because lower sums will just take way too long, and I don't want to put you guys through all that misery. So, let's get started. Now, the lower sum, or the upper sum for this, will just be what we will be finding. Now, let me write down the equation that we will be solving. It will be lim. So in this scenario, we will not be given a graph, because I want to first try and explain how to do these types of problems without a graph. And just by doing them, when one of our values, n, is not given, the number of rectangles. I equals 1 for 24 I over n squared. So this, okay, it looks like a lot, right? Looks like it might be causing some trouble, but trust me, it's not that bad, okay? So actually, we won't be using any of these sums at all. We'll just be solving this by hand because we're not given any graphs and we don't need any of these top left equations because we're already given the equation that we're supposed to find. So this is the second part of what we will be eventually trying to solve. So this is just some basics that we'll be solving. So lim as n approaches n approaches infinity, and we're solving this Riemann sum. Now you might be thinking, well, I have never seen when n is not given. Well, let me go over it, alright? So it's basically saying as I equals 1 and keeps on going on and on and on, it will end at eventually number n. And as n is approaching infinity, n will never end. So that means I will constantly be increasing and we'll never know when I will end. So we don't know the ending value, but we do know the initial value. So this is important to keep in mind. So that means that both of these values, we don't exactly know what it is. So we'll not be coming up with a numeric answer at the end of this problem. We'll be finding a problem in words of n. So we'll only have one variable left over at the end of this problem. We'll not have I anymore. We'll only end with n. So let's get started. Okay, first things first, we want to remove the scalar. So what we will be doing is first do n approaches infinity of, we're going to do parentheses just to keep track. We want to remove the scalar, so we're going to do 24 over n squared. Because what we're trying to do here is trying to remove the numbers as well as n, remember only n, outside of the Riemann sum because we want to only focus on I when we're looking inside of the Riemann sum. We only want one variable because then it'll make it easier, and that should be the initial variable at the bottom. So I equals 1 and I. Now this looks much more manageable because this 24 over n squared will just multiply to what the Riemann sum of I is. And recurring from last video, we know what Riemann sum of I is. It's just n times n plus 1 over 2. This is what I is in Riemann sum. So we will use this to just plug and chug inside of this equation. Alright, it's pretty simple actually. So we will do 24. Actually, don't forget the lim. It's really important near the end of the problem. You'll come to see why. Okay, 24 n squared. Actually, I lied. At the end of the problem, we will come up with with a numerical answer, but it'll be by using the limit function, the limit. So without the limit, we wouldn't come up with a numerical value, but with the limit, we will. So we're essentially finding the horizontal asymptote in a way. So now we will do 24 over n squared. Looks about the same from last time, but now we will be multiplying this by we will now be multiplying this by n times n plus 1 over 2, which is what was up there, right here. Because it's essentially the same thing. So now we'll just multiply. Let me get rid of some of this space. Actually, I can wait. Okay, so we'll move up here now. Change colors. Okay, so it's going to be, let's first evaluate the right. So it's going to be n times n plus 1 is n squared plus n, which is essentially just this part. We're just distributing the n over 2 times, we're going to forget the limit for now. I don't want to, it's too much for drawing. We'll just bring it back later. So we'll do that. Now now we have to multiply them. So as you can see, n squared cancels out the n squared from the denominator and the numerator. So they cancel out. Actually, you can't do that. I apologize. You can't do that. You can't do that. Alright, let me tell you why. You can only do that when n squared is multiplied by n. You can't do it when it's not. So that's why we will actually not be doing the subdivision. We will actually just leave it as n times n plus 1. And let me tell you why. This is because now we can subdivide the n on both of them since they're factors, n and n squared. So I apologize for trying to factor them or trying to distribute the n, but that's not how we do it here, alright? So what we want to do is now we can remove the square and we remove this n because n squared is just n times n, and n, you just divide n by both sides and it'll just be n. It will remain n on the denominator. So it will be 24, it's a little confusing in here, 24 times n plus 1 over 2n. Move that, it's going to be 12 n plus 12 over n, or 12 plus 12 over n, as limit of n approaches infinity of this. So let me explain how I got this. Alright, so first cancel out the 24 and 2. 24 divided by 2 is just 12, so I just did 12, so I just replaced it with 12 times n plus 1 over n. So now I just distributed the 12 to n and 1, so it's down here, 12n plus 12 over n. Now I just did 12n, so then I just did 12n over n plus 12 over n. I just split both of these down the middle, took out the n, and then we're left with 12 plus 12 over n as limit of n approaches infinity. And as we know, 12 or any number over infinity will just correlate to 0, so the answer is 12. Because if you approach n, if n is approaching infinity, it will constantly get bigger and constantly get closer to 0 if you look at the graph. So this will just cancel out to 0. So 12 plus 0 is 12. We did that now. So we did most of the basic stuff. Now we'll do the hardest problem that we'll see here, and it's going to be a little bit longer, unfortunately, but it's fine. You guys can probably stick around for a little bit longer, just for the fun of it. Let me double check this answer, just so I'm not giving you guys some false information. Alright, let's get back to it. That is right, by the way. Now let's get with the last problem that we'll be going over. And this will be a much more complicated problem, unfortunately. So we will be doing something that combines both of the previous examples that we did, including the graph and the lower and upper sums, as well as the Riemann sums, as n is undefined. Or n is, like, we don't know what n is, alright? So let's get started. Now. Okay. We will be doing this type of graph. This will end at 1, 1. And this graph is, can you guess? Probably can't, but this is just the x cubed graph. You probably didn't guess that, and I don't blame you. This drawing is absolutely horrendous. and then it starts at just 0, 0. This point right here. Now, what we are trying to find is just the area down here, okay? And we'll use that using the upper and lower sums. So, you might see something different from the first problem that we did in this video. Well, let me tell you, you're right. The problem seen here is we don't know how many rectangles we are given. Well, that's what we're trying to do. We will be finding n rectangles under the graph, and that will require us to use both of our formulas. So, let me explain. Alright. Sorry. Okay, so we want to find, obviously, the area, and the area is length times width. We can find the width pretty quickly since we know that the interval is between 0 and 1. So, we can do the formula delta x over n. Delta x is just this first one minus this second one minus this first one, which will just be 1. So delta x is 1 over n, since we don't know how many rectangles there are, and n represents how many rectangles are under the curve, so that's just going to be n. So this is the width. Now, we found what the width is. Now we have to find the length. And to do that, we will be using the upper sum because it's always easier. Okay, it's always easier. I don't think there might be many ways where that it's most likely always going to be better, because I don't think I've found any ways that it's not better. Alright, so we'll be finding the right endpoints, which, yeah, we'll be finding the right endpoints. That's it. So let us do that. Now, big S is equal to x, which is what we'll be plugging in back to this equation. So big S is equal to x, which is equal to this equation at the top left. I'm highlighting it right now. A, which is just the first value in the endpoint list, which is just 0 plus I times delta x. And in this scenario, delta x is just the same thing as the numerator of the width, which is just 1 over, you guessed it, n. So this means that this is equal to I over n. Now, you might be wondering, we literally have two variables in our equation. How are we going to solve this? Well, this is where we use Riemann sums. And this is where it gets a little bit more complicated. Not too much, hopefully. So, alright. Now, the Riemann sums, we will just be using the area formula, essentially. So, same process. We do the width, which is the same everywhere, so it will just be 1 over n. Now, we need to find the sums of all the lengths, which is a little, actually, no, we want to do this the right way. I want to show you guys the whole way. So we first actually got to draw the Riemann sum. I equals 1 and n, since we don't know what number of rectangles we're doing. So we'll do, this might not be uniform to do the width outside of the inside of the Riemann sum, but I want to show you guys how we're going to do this. So the width 1 over n times all of the lengths, which are calculated through I over n. But the problem is we didn't plug it back into the equation that we were given. So let's do it. Y equals I over n cubed. So now we know what that is. So we'll plug it into this equation, and we are given I over n cubed. Okay? Now, you might be wondering, what do we do now? Well, like last problem, we want to get rid of the scalars. Well, the scalars in this scenario are always going to be n or numbers, just pure integers. So we will first be distributing this cubed right here, alright, because we want to just get rid of it. So it's just going to be I cubed over n cubed. And to save time, I'll just, instead of drawing the full Riemann sum, I'll just draw the sigma notation to represent it. But everything's still there. So times 1 over n, like that. Actually, going to do parentheses because that's more formal. And now we did that. It's equal. So now let's just multiply all the values together. So it's going to be I cubed is over n to the power of 4. So now we want to, okay, I forgot to draw the Riemann sum, sorry, or the sigma. So now let's draw the actual the Riemann sum over this, since we simplified all of it, and we can move on. So it's equal to the area. So now you might be wondering, what do we do? Let me just clear up some space. What do we do? Redox, what are we supposed to do here? Well, let me explain. We will now be taking out the n, because that is a scalar function. So we will be doing Riemann, the sigma notation is the same thing of I cubed over 1 times 1 over n to the power of 4. Now, we have everything separated. And so, like from last video, you should remember the formula for I cubed is, I'm going to draw in the bottom right, it is n times n plus 1 over 2 whole squared. So I'll just simplify it to n squared times n plus 1 squared over 4. So this is what we're looking at. Circled thingy right here. So this is the cubed formula. Now that we know that, we will now be plugging it back into the equation. So now we know that the Riemann sum is I equals 1 to n is just of I cubed is just this formula right here. So we'll just plug it in. Equal to 1 over n fourth power times n squared times n plus 1 squared over 4. Now we can simplify a couple things. So n squared over n to the power of 4 is just equivalent to n to the power of 2 in the denominator. And yeah, that's all we can simplify for now. So we'll do n plus 1 squared over 4n squared, since we just multiplied these two together. I'm going to clear up some more space down here. So now let's get continuing. So bringing this equation to the right, we will be attempting to make this more cleaner. And to do that, we will actually be doing n plus 1 whole squared. We'll be simplifying that to n squared plus 2n plus 1 over 4n squared. Now we want to separate all of these terms so that's more easy to simplify. So we'll be doing n squared over 4n squared plus 2n over 4n squared plus 1 over 4n squared. Now we can get rid of the n squareds. We can do 1 over 4, get rid of the 1, and this will just remove the square for that. So this will be plus 2 over 4n plus 1 over 4n squared. Now, this is what the Riemann sum is equivalent to. This is a simplified version. Now you might be wondering, what do we do now? Well, so this is essentially what the area under the curve is when we don't know what the rectangles are, right? We don't know how many rectangles there are. Now, there's another step to take for this, and that is by finding it through the limits. So since we already know what the since we already know down here what the limit or what the equation is for the area under the sum or under the curve, we just need to find the limit definition for it, so that so that we can find its true definite value. So we can find the area of the region under the curve, or bounded by x cubed, which is official definite or official way of saying it, I guess. So we just got to find the limit as n approaches infinity of this. So 1/4 plus 2 over 4n plus 1 over 4n squared. Plug in n for infinity in all of these. This cancels out for 0, because anything with infinity in the denominator will just cancel out to infinity or 0 when there's an integer on the top or a number. So yeah, and so that means that this will be equivalent to 1 over 4, which is our final answer by finding the area through the limit definition for this problem when the f of x is x cubed. And the official way of saying this is the area of the region bounded by the graph of f, the x-axis, x equals 0 and x equals 1, is 1/4. Thank you guys for watching, and we are done. Please like and subscribe, and thank you.